All right, welcome everybody to lecture 17 to Intro to Machine Learning, DS 4400. This is a Northeastern class, and I am Professor Wu. So today we're going to talk about this concept called the covariance matrix, as well as the principal component analysis, or also known as PCA. So principal component analysis, okay, that's the topic for today. So far we've really focused on supervised learning, which we started off with learning regression with the mean square error. Then we learned a bunch of classification algorithms, such as logistic regression, k-nearest neighbor, SVM, decision tree. So those are the ones that we have done so far. And the idea of supervised learning is essentially that you have some kind of data, and you have some kind of label. And very often we're trying to find a function such that you can input the data and output the label, right? If you learn this function, then it works pretty well. Today, we're going to look at the most famous, I dare say most famous, under unsupervised algorithm. And the difference between supervised and unsupervised is that in unsupervised setting, you still have the data, but you no longer have label, right? You just have raw data. You don't know anything about the data, right? And you're trying to do something with it. So principal component analysis only looks at the data, and what it does is that it tries to reduce the dimension. You may have a data with very large dimension, and by reducing it, you can run it much faster. And when you reduce the dimension, you might also remove unnecessary noise. Okay, so like I said, this algorithm only looks at the data without the need for any labels. This algorithm essentially compressed the data by keeping the most important dimensions. So if you start with 1,000 dimension, you might end up with 20. So to understand PCA, there are a bunch of prerequisites. So today we're going to cover the prerequisite, like how do you do centering, and the concept of centering matrix. The concept of variance and covariance we covered last class, but we need to kind of combine them. And when you combine them, you got this thing called covariance matrix. And then once we are done with the covariance matrix in both summation and matrix format, we're ready to do PCA. So, centering. We've done centering many times actually in this class. Essentially, I'm going to define centering x hat as if you take the data and you minus the average, right? So basically, you have the data x, right, where each dimension of the data, you find the average, x bar, you find the x each dimension, and then you have the total average. Now, if you take every single sample and subtract the weighted average, that's centering. You've centered the data. And this is what you've learned so far. For example, right here, we have data. We take the average of the first column, which is the first dimension, which is 4/3. And the average of the second is 3 divided by 3. It's just 1. Okay? So you take the data, and for each sample, you subtract the average. You subtract the average. You subtract the average. So you're kind of repeating the average multiple times, and you're just subtracting it. This is centering, and I have no doubt that you guys should know what this is. Now, if there's any doubt why we call this centering, it's because you start with the data, and after you subtract the center away, it moves the data towards the center, like this. Okay? Now, today we're going to cover the second way to do centering, which instead of just subtracting the center, we are going to multiply x by a matrix. And then the result is basically x being centered. So doing this is equivalent to what we just did. But the trick is, how do you know what this centering matrix C is, right? So we're going to start. We're going to start by defining a matrix where each row is a sample. Okay, so So this is a single row, and each column is the dimension. If this is the case, then when we want to do centering, how do we go about finding the center of this, of each dimension? Well, one way to do it is we look at this as a column, and then we multiply by a 1 vector. When you multiply by 1 vector, you're essentially summing up the entire column. And if you divide by n, then you are finding the average. So this right here takes the first column, sum the whole thing up, divided by n. And the result is the average for dimension 1. Okay, so this is the average dimension 1. Now, if you were to do this again for the second column, third column, fourth column, then you're going to get the average of each column. Now, once you have it in this format, we can actually just pull 1 over n out. And we can pull this out as well. So this and this are actually equivalent. Over here, each column is equal to this, right? And then we can pull a constant out. And we can also pull a constant vector out. So once we pull these out, which is 1 over n in this one, and a vector of 1, well, notice this is just our original x. Okay, so this is the original x, which tells us I'm going to represent this vector with this symbol. Okay, so this is the 1 vector where each element is 1. This implies that we can rewrite this whole thing as 1 over n 1 times x, because this is just x. So we can, what I'm saying is we can essentially find the average. So this is what we're doing here. Like we took the average of each column. So we can get the average value for each column using this equation. Now, normally we like to represent the average value, any vector as columns. That's why I put a transpose here, because this is not a column format. So we know how to find the average now. Now, if you remember, to find the average, to subtract away from the center, so we found the average. If we want to subtract away the center, then we take the original data and subtract the average every single time. For every column, we subtract the average. Okay, so that's how we did it previously, right? If we want to find, if we want to center this, we have to subtract the average for every single row. Now, this right here is repetition. So you're copying the center, the average values for every single row. And you can mimic this copying this way. So if you have a 1 vector here, right, and over here is the center. Notice how when you take the outer product, you end up just making copies of each other. Okay? So I hope you remember how to take outer product. But if you take a second and look, they are equivalent. That when you take the outer product between 1 and this centered vector, then you are essentially making copies of it. And once again, this means that I can write this as the 1 vector again. And I know what this was. This came from right here, right? So I can combine them together. So here's the 1, and then I put this right here. This means that our centered data, like after centering, could be rewritten into this format. Okay, well, this is a constant, so I can pull this out, resulting in x minus 1 over n, 1 transpose x. Okay? Now, what is this? This is a vector of 1s. And this is a vector of 1s. transposed. Well, if you have a vector of 1, multiply the outer product of vector 1, that gives you a matrix of 1s. Like that. And we can represent this a different way. So we can represent this, right, as a vector of 1s, but we can also do this. So this is now n by n matrix. So we can rewrite this way. Basically, I just combine the two 1 vectors together, right? And oh, I didn't write it this way, but you get the point. In any case, now you can pull x out. So x over here, x over here. So now you have x. This means that x multiplied by this right here, by this matrix, which I'm going to call the centering matrix, will center the data. So this right here centers the data. From this derivation, we see that this right here is the center data. I mean the centering matrix. So this is the identity, 1 over n, and this is the 1 matrix. So this is the second way to essentially perform centering. Now, I would like you to pause the video and convince yourself. So previously, we calculate centering this way, right? This is the good old-fashioned way. Now, see if you can use this here, identify what the centering matrix is. Once you identify the centering matrix, multiply by x, and you should get exactly the same result because they're the same. So pause the video, do that, and we're going to move on. Now, with centering matrix, there are two properties. The first property is that centering matrix is symmetric. And the second property is that centering matrix, when you multiply it by itself, it actually gives you the centering matrix back. Because if it's already center, you try to center it again, then you're just doing nothing, right? So centering twice, if you move the data to the center, and then you try to move the data to the center again, it's equivalent to just moving the data to the center in the first place. Hence, if you try to center it twice, right, it's kind of like this, XCC, right? You center it, and you try to center again, nothing's going to change. Therefore, 2 centering is equivalent to 1 centering. Now, for those two properties, once again, I want you to pause the video, right? Here's a centering matrix. See, test, and convince yourself that these two properties are indeed true. Okay, pause, and we'll go from here. Okay, the next idea we need to cover is multiplication with vectors of vectors. So let's say we have 4 vectors, x, y, w, z, right? Well, we can one way represent x, a matrix, as each row is the vector. So x transpose, right, as the row, y transpose as the row. So here's x. We can represent this matrix this way. Now, what is interesting about representing the matrix this way is that you can also view this as a column vector. So now x is no longer a matrix. It's simultaneously a vector of vectors. Okay? It's a vector of vectors. So now you can treat each element as if it's just a number. Now let me define another one. Right here, you can picture it's a vector of vectors. So y right here is really a matrix. But if you let each column represent by just a symbol, you can actually view this as a horizontal vector, right? What is interesting about viewing matrix this way is that once you view the matrix this way, you can perform matrix multiplication as if it was vector multiplication. So x and y, right? Here's x right here. Here's y. Now, if you perform an outer product here, outer product, treating each one of them as a scalar, you will actually get the same thing as if you were multiplying matrix multiplication. So if we do the outer product here, notice this, basically this vector multiplied by this, right? You see that? By x. And then you take this vector multiplied by y, this vector multiplied by y. So this is the outer product. If you were to multiply this out, it would work. This would actually be the same as if you did the matrix multiplication. Conversely, that was xy. You can also do yx, right? So now this was the outer product, but now you're performing inner product. And when you're performing inner product, the result will end up looking like this. And guess what? This will be equivalent to if you had multiplied matrix multiplication. Now, let's test this idea out. Well, here's the x1, x2, right? And therefore, x is just 2 rows. Okay? If we treat x as a vector of vectors, right, then x transpose x will equal to x1, x2 times this. Now, if you were to do the dot product here, you're going to get x1 transpose, x2, x2 transpose. So you should take this, multiply this out. Okay? Take this, pause the video. Okay? Pause the video, take it, multiply it out. And then just take the x and then do the matrix multiplication. The two of them should be identical. Do this just to really convince yourself that you can not only do matrix multiplication, you can treat matrix as vectors of vector. And in those cases, matrix multiplication becomes vector multiplication. Okay, so do this, pause the video, and convince yourself of this idea. All right, so next, the knowing that you can treat vectors as elements of matrix, right? For various, this allows a lot of possibilities. It makes life a lot easier in so many ways. Like it allows us to, for example, convert summation into matrix format. For example, let's say we have this x here, right? And we have this summation. Well, this right here, this summation will be kind of a pain. You have to program, you have to write a loop and then sum it through, right? It will sum them. But notice this is x1, x2, xn, right? Therefore, if you can just write them as if they're elements of a vector, right? And then if you multiply this, notice the dot product. When you do the dot product here, well, this dot this is just this. And then the second one dot this one is just this one. So the dot product here, the summation, notice how by essentially us viewing matrix as vectors of vectors, it really simplifies a lot of the operations. And therefore, what is this? I told you this is just x. So this is just x times x transpose, right? So now what we did is we convert this summation into like matrix multiplication. Now think about how much easier, like what kind of code you have to write if you were to essentially write summation versus you just do one single like dot product. So your understanding and your ability to view matrix as vectors of vectors is what will allow you to convert a lot of these summations into matrix format. And you can essentially like organize your data. It makes your life so much easier. Now, let's combine this idea, right? I just told you summation right here is equal to this, right? Now, what if each element is subtracting away from the center. Okay, so we did the centering before. This is actually equivalent to if you had taken x centered times this. Okay, I'm going to denote this as x bar transpose x bar. So you can calculate this, right? The multiplication of x minus the centering, right? Basically just with the dot product. And this is like very, very powerful. And we can further simplify this. If we put the transpose inside, right, then we flip, it'll be x transpose c transpose right here. And I taught you previously that c is symmetric, and when you have c transpose times c, that's just equal to c self. Therefore, this matrix is this summation is equivalent to this matrix multiplication. Much easier to deal with. Much easier. Okay? You rather be doing this than this. Okay, let's extend this idea further, right? So this was x minus x bar, and I told you this is equivalent to x transpose centering matrix times x, where x was defined this way. Now, following the same logic, we can have x minus x bar, y minus y bar. Well, where x is defined this way and y is defined this way. So you should not be surprised that if we have this formulation, then this, right, I'm going to write this as x hat I, y hat I. So that's equivalent to this here. And now we can pull this out. So this is, again, just a dot product, right? This is just a dot product. Now, if you can do this, well, what is this right here? It's just x-centered. Over here, it's just y-centered. Now, we can move the transpose in. So it's x transpose, c transpose, cy. And now, c combines into 1. Voila. We can write this summation. And this n could be a very large number, right? So this like 1,000 summations into one single matrix multiplication. Again, makes your life a lot easier. So now that we covered these basic ideas, let's go over the concept of variance and covariance again. Now, the concept of variance, well, it's just this equation. And guess what? This equation right here can be written this way. Well, if you look at this, there's a lot of similarities. There's a lot of similarities between covariance and all the math we just did. Okay? Now, variance and covariance is just xi minus x bar and y minus this. So I would like you to start looking at these from a matrix perspective. These are summations. However, these summations can be rewritten easily into matrix format. Okay? So the key here is these are just scalars. Of course, we're going to deal with higher dimension stuff. So you also learned previously that the covariance with itself is just variance. Because, well, if this is x and this is x bar, then this is the same as that, right? Okay, so now that we've reviewed very quickly the concept of variance and covariance, now we're going to talk about this thing called covariance matrix. This is something new. Well, with covariance, we have two variables, x and y, and we're trying to find the covariance between them, right? Which is essentially the dependency. But what if we have more than two? Then what do? How do we summarize the relationship between multiple right? That's where the covariance matrix comes in. So in this particular case, we'll use the example where there are three, right? More than two, three. And three data sets. And each one of them like one dimension, so we can view each one of them as a data set. The covariance matrix is a way of summarizing the relationship. Okay, so how does it summarize? Well, let's say this is data 1, data 2, data 3, and each one of them is a column. Well, the covariance matrix, what it does is that it finds the covariance between x1, 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 x2, x1, x3. So you're essentially finding a covariance of every combination of x1, 2, 3, right? Now you have x2, x1, x2, 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 x3. So you're finding the covariance. So right now you have a three variables. Therefore you get a 3 by 3. You can imagine if we have like x all the way to 10, right? 10 variables, then the covariance matrix would be 10 by 10. Now I told you previously, the covariance with itself is just the variance. So all the diagonal ones are going to be the variance, and all the off diagonals are the covariance with some other variable. So this is covariance matrix. Like this is it right here. Now, calculating, like understanding what it is and calculating is a different story. The covariance matrix, right? If it's 10 by 10, you have to calculate 100 times, like because there will be 100 elements in here. And if you learn anything, is well, trying to do that will be really, really painful. You don't want to put it in a loop and do 100. What if you have 1,000, right? Then it'd be 1,000 times 1,000. That would be a huge number you have to loop through. Well, there is an easier way, right? Because everything we learned so far is if you convert like a bunch of operations into matrix format, they become just matrix multiplication, and it's a lot easier. So instead of calculating this, consider if we multiply this instead. Okay, so when you multiply this, well, notice this, I'm going to represent it again. Where this is the average. So this is already has the center move. Okay, so center is already moved. And I'm going to represent each row as an element. And here I'm going to do the transpose of it. I'm going to represent each column as an element. And this essentially allows us to perform matrix multiplication as if they're vectors. Now let's do the outer product. If you do the outer product, it will look something like this. Okay, let's further divide this up here. Well, this with the hat, remember I told you it means it's minusing, already subtracting the mean. So this is equivalent to the summation of this. So it's because, well, remember when you take the inner product, right, is equivalent to summation. So notice this is equal to this, 1, 1, and then this one's 1, 2, 1, 2. This is 2, 1. Oh, there's some typos. This should be 2. This should be 2. This should also be 2. Yeah, there's some typos. But in any case, you'll end up getting a form that looks kind of like this. And guess what? This right here is exactly the same as variance. Covariance between 1, 1, and this right here is covariance between 1, 2. This should be 1 here. So I think there's some typos in here, but you get the point. The point is when you actually multiply this out, you get the definition of covariance, and you end up getting the covariance 1, 1, covariance 1, 2, covariance 2, 1, and so on and so forth. And therefore, if X is a matrix, you can just call this the covariance of X, where X has three dimensions. So that's the covariance matrix. And guess what? instead of calculating them one at a time, covariance one at a time, you can just calculate it this way. This is it. That's all. It's just X transpose CX. And if you have the empirical version, this is what you have. So this is, again, much easier than if you try to do it one at a time. Now that we've covered most of the basics, I think we're ready to talk about PCA. So principal component analysis. Well, very often we have some data, and the data has a high dimension, but even though it has high dimension, a lot of them are not really representing anything, right? Therefore, after PCA, we end up getting a different data that still represent basically the same information, yet you compressed it into like fewer dimensions, right? So the idea of PCA is essentially you have some data like the green dots here, and what you want to do is you want to find a direction, a vector, such that when you project it down, right, you end up getting this. The data after projection, you want it to look as similar to the original data as possible. So imagine if we had picked a wrong direction. So this was the right direction. If we pick the wrong direction, after the projection, we're going to get this. Does this look like the original data, or does this look like the original data? So the idea is, even though you've compressed it into just one dimension, right? Because everything here is on the line now. Because it's on the line, it's just really one dimension that's representing it. You've also compressed the data here onto one dimension. But when you compress it with the appropriate projection, the data looks very, very similar to the original. Therefore, you basically didn't lose much. But over here, you've lost quite a bit. Like over here, like this looks nothing like this now. So this tells you the importance of finding the projection line, V. Okay. Now, the key insight to PCA is that if after the projection, you have a very large variance versus a very small variance, the larger one is going to look more like the original data. That is the insight. That's the key point. That after projection, then this is what happens. Now, how do you do projection again? Well, let's say if we have x1, right? Well, if you want to project it onto this vector v, and we're going to assume v is it's a normalized. Well, the way you will do a projection is this times v, right? And this will essentially tells you the distance from here to here. And since it's just one dimension, you only need the distance. And then what you want to do is project the second point, and then the third point, right? So each one of them would tell you the coordinate. Now, instead of doing them one at a time, we can make this your life a lot easier if we just write x1 transpose, x2 transpose, so on and so forth, times v. So what is this? This is x. This is original data, x times v hat. And that's it. Like, this is how you can essentially project every single point onto the line. Just stack the points up as x and then multiply v on it. Now, how do you measure the covariance? Well, if you have the data x here and then you project it, so this will be the data after the projection. Okay? So after the projection, the data, and then what you want to do is measure the covariance. Now, what I told you is the insight to PCA is you want the covariance to be as large as possible. So what we're doing is we want to find the V. We want to find a direction such that the covariance is as big as possible. Again, look at this plot. If you pick the correct direction, notice after projection, it looks like the original data. if you pick the wrong projection, right, after the projection, it looks nothing like the data anymore. Okay, so that's the insight. And therefore, this is the objective we're trying to solve here. The objective is you want to pick V, right? Now, from SVM, I think we learned that picking a normalized vector is not easy. And therefore, like, we're going to talk about how to solve that. But first, we already went over the how to obtain the matrix format for covariance, right? So this right here, assuming it's centered, well, let's just write this. This is equal to this because this right here is the covariance matrix, and this does the centering. So we did this. Now, this is for covariance x. What happened if we want the covariance of x times v hat, right? If this is the case, then for every x, we got to write x v hat. Therefore, x v hat here, v hat transpose x here, right? So all I did is for every single x, I wrote x v hat. Okay, so what we are solving now is essentially this. We want to find the v. We want to find the v that makes the covariance as large as possible. Okay, so again, you can't find v hat. So what PCA opt to do, like they decided that you can find it. There is a way to find an orthonormal one. Sorry, to find a normalized one. Well, if that's the case, well, we can add a penalty term. And the penalty term essentially says that you want v times v to equal to 1, normalized, right? And therefore, notice if it's not equal to 1, it's going to lower the objective, which is not what we want. We're trying to make it as big as possible. So we can add a penalty such that if v doesn't match, like it's not normalized, then it's going to hurt the overall objective. So that's how PCA essentially solve the normalized version. And now they just find v, any v, with the penalty. So notice this is v hat and this is v. Okay? Now, this right here, we know the data, we know the center matrix, so we can multiply them out, resulting in Q. I'm going to call, after multiplying them out, I'm just going to call it Q. And here is the final form of the principal component analysis. Okay, so how do we solve this? Well, to solve this, we can traditionally using gradient descent, right? But for this particular case, we got lucky and we don't have to anymore, right? For PCA, we can simply take the derivative and set it to 0. It makes life so much easier. We don't have to run gradient descent. Now, I hope you remember how to take the derivative. The derivative of this is just 2qv, and the derivative of this, right? This v is equivalent to v transpose identity v. Therefore, it's 2 identity v. Right? And it just, therefore, that's how I got this. Okay, right here. Now, we just set this to 0. Right? If we set this to 0, right, this cancels out. This is equals to 0. 2 cancels out. We have qv equals to lambda v. Right here. And guess what? If you have done linear algebra, you will recognize this is the definition, the actual definition of eigenvalues and eigenvectors. And what it is saying is the v must be the eigenvectors of Q. And lambda must be the eigenvalues of Q. Now, from this solution, we know that v and lambda, again, must be eigenvalue and eigenvectors of Q. And and that's it. Like the rest of the question is, since a matrix can have multiple eigenvalues, eigenvectors, which one should you pick, right? Well, that's also easy. That's also easy to answer. Now remember, we're trying to maximize this, right? And if you remember from linear algebra, eigenvectors are always normalized. So you don't even have to worry about this anymore. So we just need to worry about maximizing this. And the second is, remember, I said it, eigenvectors are orthonormal, implying that when you multiply, I said it, this is already satisfied. This will equal to 1, and therefore this whole thing will be canceled out. So if you remember these two, then we can look. How do we maximize this? Well, this, by definition, is equal to this, right? So I'm going to plug that in. And since lambda is just a constant, I can move the lambda outside. And since V transpose V is just equal to 1, then it's just equal to lambda. So by picking the eigenvector, right, we know, depending on the eigenvector we pick, we're going to get, it's going to equal to the eigenvalue. Therefore, if we pick the eigenvector with the largest eigenvalue, that eigenvector must maximize this objective. Okay? Again, we want to pick the eigenvector with the largest eigenvalue, right? So once we do that, we maximize the objective and problem solved. All right, so here's an example. Like here's a two-dimensional data where we have the x and y. And in this example, we're going to reduce it down to one dimension. Okay, so here's a centering matrix. If you remember the definition, we can just fill it in. And then all we have to do is calculate Q. So after we calculate Q, which is equal to this, right? So X is equal to this. And with X and the centering matrix, our result Q is equal to this. Now you need to calculate the eigen decomposition. So lambda 1, 0.95, and here's the eigenvector. And the second one, 21, and here's the eigenvector. Well, from this, remember you want to pick the largest one. So this eigenvector is the solution, right? Now, if you were to draw this vector out, 0.67, which is right here, and 7.4, yeah. So this is the vector. Notice how the vector is essentially this line that gives you the perfect projection, so that the data is going to basically look like very similar to the original. Okay. Now, once you have V, you can obtain the low dimension by just multiplying X and V, right? This is how you multiply this by this. That's how you do projection. And once you multiply them together, the new points are here. So essentially, we took two-dimensional data, move it to one dimension. And notice if you draw the lines down, like here, it would be like this, right? So we moved it down to just one dimension. Now, right now, I showed you guys reducing down to one dimension, right? When you do one dimension, it's essentially x times the vector, right? This is performing projection, where x hat is the data after the projection, okay? But if you want to project down, like you don't always just want to reduce it down to one dimension. Maybe you want to reduce it down to multiple dimensions, right? To do this, we will then need to project down to multiple vectors, not just one. We need to project multiple times. And then this will result in 3 dimensions. So this example, having 3 vectors, will give us, right, a residual dimension of 3. Now, if V1 is the eigenvector of the largest eigenvalue, then what do you think V2 and V3 should be? right? Well, it's not going to be surprised, right? Since the solutions are always eigenvectors, well, V2 should be the eigenvector with the second largest eigenvalue, and V3 should be the eigenvector with the third largest eigenvalue, and so on and so forth. So that's how you can essentially reduce the data down to multiple dimensions. Now, that a natural question then arises, if you have like 100 dimensions, how do you know how many dimensions you should reduce down to? Well, that's also very easy to figure out. To answer this, you first need to understand the actual meaning of eigenvalues and eigenvectors. First, eigenvectors are the directions, the various directions that essentially represent the data. And this should be value. Eigenvalues is associated with the eigenvector. Each eigenvector is associated with its own eigenvalue. So it looks like this. This eigenvector has an eigenvalue. This eigenvector has a. So this association has a significant meaning. The meaning is that the eigenvalue tells you the contribution of the eigenvector towards representing the data. Therefore, if you have the pair that looks something like this, 10, 7, 0, 0, 0, what this is telling you is that only these ones are contributing to representation of the data. And these vectors are not contributing towards the representation of the data. Therefore, you can just actually ignore them, and you can still, because these ones have zero contribution, right? Therefore, you only need these two. Therefore, by looking at the eigenvalues, well, we know exactly when to cut it off. Namely, the eigenvalues, when the eigenvalues are getting, it doesn't have to be 0. It could be like 0, 0, 1. And you're like, oh, that's too small. Not worth keeping. So you cut it off. So you can look at the eigenvalues and know when to cut it off. In this particular example right here, well, notice that there isn't a cutoff. Each one of them, each direction, each vector is contributing. Therefore, this would be a bad candidate for PCA. All right, when you see this, you look at the eigenvalues, you're like, I don't think. So don't perform PCA, just reduce the dimension of the data for the sake of reducing the dimension. You need to look at the eigenvalues so that you are making sure you're not just blindly removing the dimensions that you really should be keeping. Okay, so that's the key point here. So by looking at the eigenvalues, it tells you the contribution. Okay, so I wrote the code for you guys to essentially perform PCA, right? So you can perform eigendecomposition on that Q matrix, and then you can essentially find the eigenvectors. Now, all these is essentially how you perform it by code. In sklearn, PCA is as easy, again, as just one line. The number of components tells you how many dimensions you want to reduce it down to, right? Then, voila, you get the result. So this right here is PCA. All right, so I think this is the last slide. Here's the data, right? Here's the data. I want you to do it by hand and essentially figure out the appropriate direction, the best direction to do the projection that give you the least amount of error. So you want to identify the centering matrix, calculate the covariance matrix, then you can find an optimal solution from eigendecomposition. Okay? Once you solve it with Python again, right? And then you should get I think you might get different answers. So you want to figure out why your answers might be different. So okay, that's it. I hope that was helpful. I will talk to you guys in the next lecture.